This means EE544 discussion on Friday, January 31st, 2014.
All right, here we are. So if you remember last time I did the transistor stuff, I talked about the structure, the physics, and then the mathematical descriptions that we use for DC analysis. Oh, right. And so today what I'd like to do is tie some of the frequency analysis stuff with circuits and then transition to transistors in what we call the small signal model, which is what we use 99% of the time when we're talking about radio frequency stuff and amplifiers and that kind of thing. So to start off, let's consider a capacitor. So the current voltage relationship for a capacitor is like this. And so to kind of review some frequency analysis stuff, let's find the frequency. So this is in time. And usually when you talk about a capacitor and you start writing equations with the capacitors, you're actually working in the frequency domain. So I'm going to go ahead and derive that frequency domain relationship really quick. So I'm just going to take the Fourier transform of both sides. So my current in the frequency domain is just the integral from minus infinity to infinity I of t e to the minus j 2 pi f t dt. That's pretty straightforward. You have to know the form, obviously, of I of t, but you can write it just like this and be done with it. So that's the left-hand side. When it comes to the right-hand side, I now have the integral from minus infinity to infinity c times the derivative in time of the voltage, whoops, e to the minus j 2 pi f t dt. So now this is a little bit more complicated, and obviously I could jump straight into using one of the properties, but I'm actually going to go ahead and just derive that property really quick. So the property that I need is the derivative property for the transform. But it's actually really easy to derive using integration by parts. So if you remember, integration by parts says you have something u dv, and this is equal to the integral uv minus the integral, v du. So for this thing, I'm going to let dv equal the time derivative times the little integral part. And so that means that this variable v, is just equal to the voltage in time. And u is just going to be e to the minus j 2 pi f t. And du then is going to be minus j 2 pi f e to the minus j 2 pi f t times dt. So now just putting these I guess 5 things together, with that, I'm going to have, so my Fourier transform is going to be equal to the capacitance times the time, the voltage in time, times e to the minus j 2 pi f t, that's going to be evaluated from t equals minus infinity to infinity minus the integral c times minus j 2 pi f times v of t e to the minus j 2 pi f t dt. So now this part is going to equal 0 because for any physically realizable voltage v of plus or minus infinity has to equal 0. Just essentially it has to be 0 at some point in the very distant past and the very distant future. Otherwise it's going to have infinite energy. So what I'm left with is my Fourier transform of the right-hand side is now going to be j c 2 pi f times the Fourier voltage. And if I set this equal to I of f, I get my standard equation, which is basically this rearranged. So it's and so this is the frequency domain impedance of a capacitor. I'll need one. Of a capacitor. Okay. So there's my review of the Fourier stuff that we've done already. And hopefully a reminder of capacitors. Now for inductors, I won't go through the whole thing again. But the inductor current voltage relationship is like this in time. And so in frequency domain, it's, I'm sorry, just trying to write this in frequency domain, j omega L is I of f. And so those are the things that you'll most commonly use when dealing with circuits that have capacitors and inductors. So now let's go ahead and do an example. Oops. Of a circuit with a capacitor and inductor. There's my wonderful title. Frequency domain circuit analysis example. So in the frequency domain, we have to have a variable source, and then we just have whatever components we have. In this case, I'm going to use this circuit. So I have an inductor here, capacitor here, and some resistor here. And I'm going to look at the output here across the inductor, actually across the parallel combination of the inductor and capacitor. So if I consider that pair, so if I consider them, the impedance of the parallel combination is just going to be this. Impedance of the capacitor, impedance of the inductor, over the sum of the two. And if I just substitute in the values, the frequency domain values that I just reminded you of, it's going to look like this. So I'm going to have 1 over j omega c for the capacitor, j omega L for the inductor, and then the same thing on the bottom. So for the sum rather than the product. And then usually, to simplify, you don't usually like to have fractions in the denominator of an expression like this. So I'm going to multiply it by j omega c on the top and bottom. And that actually makes things a lot simpler. So I'm going to end up with j omega L on the top. And I'm going to have 1 minus omega squared LC on the bottom. So that's the parallel combination of these two components. So now, in order to find V out, I just need to do a voltage divider between this impedance and the resistor. So V out is going to be V in times that mess that I just made right there, j omega L over 1 minus omega squared LC over R plus the same mess, j omega L 1 minus omega squared LC. And then again, we don't like to have the fraction of the denominator, so let's simplify this. I have V in j omega L over R plus j omega L minus omega squared LCR. So that's my input-output relationship. And now, further, when we're talking about frequency domain analysis, we usually want to talk about impulse responses. And that I have a tendency to write it like this, and this j omega in the argument is, I don't like it, but every time I write it, I do that, so if you guys have a problem with it, you don't have to write it. You can write just h of omega, and that's fine. But it's basically the input, or the output over the input. And for this one that I've done up here, it's straightforward to just write, you have j omega L over R plus j omega L minus omega squared LCR. So that's my impulse response of this system from the input to the output. Now, a little bit of systems review, and then I'll get into the transistor stuff. So if I have a series of LTI systems that I can represent with just their frequency response, or their impulse response, and I apply them to an input. So this is H1, there shouldn't be a dot there, sorry, H1 j omega, H2 j omega, and my output. So I'm going to call my input X j omega, Y j omega, and if I look at what's going on here, in frequency domain, at this point, the signal is X of j omega times H1 of j omega, and my output is simply my input times the first system times the second system. Now the point in showing you this is to remind you that if I have two LTI systems, I can reverse their order, because down here in the frequency domain, I've just got a product of all three: the input, the impulse response of one, the impulse response of the second. So
the time is 21 o'clock.
This system is equivalent to this system. If I just switch the two LTI systems. And my output is going to be the same as before, because the order of multiplication doesn't matter, okay, for LTI systems. And then to write that out, LTI systems may be transposed order doesn't matter. Now, when we're working with radio systems and anything that has a mixer or anything like that in there, this kind of goes out the window, right? Because the mixer is not an LTI system. It's a multiplicative in in the signal amplitudes, basically. So it multiplies the two signal amplitudes together, and basically it creates the thing that it does to the signal is not representable by an LTI system. They produce a product of two signals. And so that the way that you kind of remember that is that if you have a filter before a mixer, it changes what happens at the output than if you put the filter after the mixer, depending on you know, what the filter is doing exactly and what the mixer is mixing with. Okay. So that's my LTI stuff. Now to transistors. So when we're dealing with frequency analysis with transistors, like I said, we're usually dealing with what's called the small signal model. And for our purposes, we're going to be mostly dealing with MOSFETs, so I'm going to do this for MOSFETs. Almost the exact same stuff applies to BJTs. You just have to find the parameters slightly differently based on the BJT formula rather than the MOSFET formula. But it's important to note that usually when you're doing small signal analysis for a transistor circuit, you're dealing with the transistor that is in the saturation region. And so the current voltage relationship is like this. So the gate source voltage minus the threshold voltage gives you this part. And then I've included the channel length modulation factor because I'm gonna use that in what I do after this. You can include it or not, depending on how much channel length modulation you actually think you're going to have. It's really kind of up to you to figure out whether it's right to use it or not. Simple analysis, you don't worry about it, but more exact analysis, you're going to want to keep that in there. So the components for the small signal model are found by taking derivatives. And the derivatives are taken with the assumption that you have some operating point DC. So DC operating point also called the Q point, assumes, for example, that IDS equals some IDS DC plus, I'm gonna make this a little IDS that depends on time. So this is if you have a signal coming into the circuit, you want to use the DC value of IDS, which is just this part, and leave the time varying part for the small signal model. More importantly, usually you have VDS, which is defined in the same way. You have some VDS, which has a DC value, and then a time varying value. And same thing for VGS. If I can just, I guess, be explicit about everything. So these values would represent the Q point, and they determine the actual parameters of the small signal model once you actually get to it. So find those small signal components by taking the derivatives of the current voltage relationship, like I said before. So here's one that is very important, the derivative of IDS with respect to VGS. If I work through the derivative from above, I get this. So the square just comes down and cancels the 2, and then this part goes away because VDS is considered not to vary in this case. So let's see. Oh, so that we usually call GM, and that is its transconductance, or a voltage-dependent current source. And basically it goes from the, so you're looking at IDS, so you're looking at something that goes from up here, the drain, to the source. And it's the value of the current going through there is this. So it's this GM value times whatever the signal component of VGS is. So another one of those that we want to look at is this one, derivative of IDS with respect to VDS. This one's a lot simpler. I left off a lot of this one. I think I wrote this down, but I think this is actually not quite right. So it's lambda times VDS, but actually it should be, if I look at this thing, it should be lambda VDS times all of this stuff, right? I believe. So all of that kind of has an effect on what this value is going to be. I'll play this through. Yeah. So I think that should actually be so this is the Q point VGS. So I think that's what that should be. Does that look familiar? Let me write this. I'll double check this one. I just realized just now when I was looking at it that that didn't look quite right. It's the derivative of this with respect to VDS, because all this other stuff should come through, when you multiply it by there. I'll look into that and hopefully clear that up for you guys. But regardless, it doesn't. For the rest of the lecture, it doesn't actually matter. Basically, what happens is this is a conductance, and it has a static value for a given Q point. But basically, the conductance comes out like this. Usually, you call it GO, and it's connected from the drain to the source. You can also deal with the conductance as a resistance, which people most often do. Okay. So now let's go ahead and do a first cut of a frequency small signal analysis. So this is a circuit I'm going to look at. Whoops. It's a poorly drawn resistor right there. This resistor is R. This one's R1. Then over here I have my signal voltage and then a DC biasing voltage right here. So this DC biasing voltage will be the one that I use to determine the Q point along with this VDD up here. So once I've done that, I need to draw the AC circuit. And I'm going to use the low frequency circuit here. Just to simplify the first one, then I'll do with the the other components that come in when you consider higher frequencies. So this particular part of the circuit stays the same. Now remember, when you draw an AC circuit from a DC circuit, remember your DC sources become AC grounds. And I think that's really the only major change, aside from substituting in the small signal model. So this is the gate of the transistor. And across here I have VGS. So this end is the source. Then I have that generator, GM VGS. And then I'm going to use it as a resistance, a channel resistance here. And then the resistor up here. So this is R, this is R naught. And my output voltage is right here across R naught. Okay. So in this case, because of this being an AC circuit and the fact that I don't have any resistors down here, R naught and R are parallel. And they conduct current GM VGS. So if I want to write the output voltage of this, I can write it pretty quickly. So it's the current. It's actually, I could have just written it instead of writing that sentence right there. Okay. Now, simple enough for this circuit, VGS is actually Vin, which I forgot to label right here. Since there's not going to be any current flowing through here because of this open right here. So that lets me write the system response for this almost directly. And I'm going to put this is low frequency. And so it's R naught parallel with R times GM. Simple enough, right? It's a little amplifier with amplification, sorry. R naught R parallel with R times GM. All right. So now what happens when we start looking at higher frequency models? We start getting more components in the small signal model. And those come from basically from the geometry of the model, which isn't taken into account as part of the DC equations which we have from before. So I'm going to redraw the circuit. For higher frequency. So the left part over here looks basically the same. It's my resistor R1. This is still the gate, but now instead of just being open, the gate now has a capacitor, CGS. This is still VGS right here. And everything else basically looks the same. So depending on how accurate you're drawing your high frequency model, you're going to have more and more capacitors. And I'm leaving out other capacitors that you may be familiar with, like a gate to drain capacitance, which would be connected right here. And I'm doing that because I'm kind of cheating, because it makes the analysis quite a lot more complex. So this is GM VGS. That's my V out. It's supposed to be taken across from here to here, but R and R not are parallel again. So actually for this one, the output equation is actually exactly the same. GM VGS R not parallel with R. It's just the fact that now VGS is different. And VGS is why I did all that other stuff before, is a voltage divider between this resistor and this capacitor right here. So it's Vn times the impedance of the capacitor, 1 over j omega c, over R plus 1 over j omega c. And simplifying, or beautifying, I guess, we get 1 plus j omega RC. So that's VGS. So I can just substitute that in right there, find that V out is equal to V in R naught parallel with R times GM over 1 plus j omega RC. And thankfully, as omega goes to 0, we get the low frequency. It's a low frequency model. So when you're looking at circuits in this course, usually this model will be good enough, unless you find out that your gate to drain capacitance is an actual issue, in which case you'll have the capacitance from the gate to the drain up here, and you'll have to consider that in calculating everything, because now that complicates everything a lot more, right? Because now the current going through this guy is partially coming from here and partially coming from here. VGS now also depends on GM VGS. So there's a lot more feedback that actually occurs. And that's exactly why I didn't include it here, is because it probably would have taken me the entire course, the entire time just to do that one. Okay, so let's continue on. I'm going to use a little bit more complicated circuit now for what I'm going to do next. It's going to be a source follower, and I am going to actually use CGD, but I'm going to talk about, instead of talking about the frequency response, I'm going to start talking about input-output impedance, and on the way I'm going to talk about some transforms that you kind of do on some of these elements to simplify them. And a lot of times what you'll see is a book will give you a certain model for a source follower, or a certain model for a common gate, or a certain model for a common drain. They all come from the same small signal model. They've just rearranged the components to make it look simpler. So let me go ahead and show you the circuit that I'm going to use, and then I think I can get through a couple of those simplifications, and then I think I'm going to have to stop. So I'm going to have a source follower. And the circuit DC looks like this. Let me start at the top. I'm going to explicitly ground my bulk. So this is RL, CL, so this is the load that I'm looking at. So my output voltage is going to be here. And then on the input, I just have a resistor, I'm going to call it the source resistor, and then I have, just like before, I have my signal and my biasing. And I'll talk about this stuff later on, probably next lecture, if I get through all this stuff. So that's my circuit. So now I'm going to draw the small signal model, which is kind of a mess. So here's my source. Here's CGS, and across there is VGS. This is gate to drain capacitance. And now we have a whole bunch of, actually I have one more thing here. Just like back here where I started taking these derivatives, DIDS, VGS, the threshold voltage actually depends on the bulk voltage. So the bulk voltage actually creates another generator. That's why I noted this, that I was explicitly grounding that. So this is another generator that comes up from the bulk to source bias. VBS. Okay. And then this is the channel resistance, R0. And then I have to mark out a couple of other things down here. So here, this is my source and this is my bulk. So my bulk to source voltage goes this way. And then I have, obviously, the load components down here. So this is RL, and this is CL. Yes? The second current source? That's what I was trying to explain really quickly without actually showing you. VTH actually depends on the bulk to source bias. So you can do the same sort of thing here where you take DIDS, DVBS, and it comes up with another generator. There's this horribly, horribly complicated version of this equation that has all that stuff in it. And so if you use that equation and take that derivative, you get this other generator from drain to source, but now it depends on the bulk to source voltage. If you really want to see it, I can bring that equation next time, or you stop by my house, or I could probably find it somewhere. It's really horrible. It's like this equation, so you write this, and then you've got like this much other stuff after it to try to account for everything else. But the reason why I'm including this in here is because when you see a source follower model, it has a component that basically comes from this. And so I wanted to try and show you that. So so this guy is grounded up here, and then there's a voltage right here that I want to mark across CGD. I want to call that VI. Sorry, I'm getting a little bit cramped here with everything I'm trying to draw. But basically, simplifications that I want to note here: VGS is equal to VI plus VBS, because VBS is this voltage from here to here, and VI is the voltage across this, from this point to ground now. So my VGS is now equal to VI plus VBS, which is actually the negative of the voltage at this point. Okay. Sue me for being complicated. I'm not trying to be complicated, I'm just trying to show you where this thing comes from. Okay. So I'm going to use complex frequency just to throw a monkey in the wrench. ZL is now SL. ZC is 1 over SC. And S is just sigma plus j omega. So that's how I'm going to write my equations. It's not really important that I do it that way. It's just to remind you that there's another way to write those things. This is basically the Laplace transform version of those things that we've seen before. So for the generator that is hooked up like this, so it goes, here is VBS, it goes down, I'm sorry, its value is lambda B, GM, VBS. And if you look at how VBS is connected, ground is the positive side and this side is the negative side. So VBS is actually from here to here, VBS. So if I look at its contribution to IDS, I have VBS over IDS is lambda B GM. I'm sorry, 1 over that. And so what you usually do is you usually just consider this to be a resistor. Because when a current source depends on the voltage across it, it's basically just a resistor. So the other generator, and this is the one that they really mess with when they try to make that other model to make it look simpler. You have this. You have GM, VGS. And now I told you that VGS can be decomposed into VI and VBS. So if I do that, I have two generators. So this one is VI times GM, and this one is VBS times GM. And again, where it's hooked up in the circuit, VBS is exactly the voltage across it. So you get another resistor. So that's VBS right there. So this guy becomes just another resistor. And the final simplification that you end up with, and the whole reason why I'm showing you this, is you have VI, GM, this resistor, which I'm going to call 1 over GM, or I'll just call it RG. So now I'm going to put these two simplifications in and show you how this turned into that model that you usually see. Okay. And when you do this, you actually end up switching the direction of a lot of things. So I'll try to note all of those when I do that. So there's RS. All that stuff's the same. Now, here's where things start to look a little fishy. I'm going to put VI here, which means that this capacitor is the gate to drain capacitor. This is CGS. So now I have my source on the top. this generator goes from the drain to the source, so it goes up. Now it's VI GM. Thank you. And then I have this whole mess of resistors now. So I have this resistor, and it turns out that these resistors are actually in parallel with those. So I have one resistor, two resistors, let's see, 1, 2, 3, 4 resistors. And finally, my capacitor. Okay. And this is all grounded over here. So CL, RL, RO. This one I labeled RB, which is, just to make a reminder here, 1 over lambda BGM, and this one is RG, which is 1 over GM. So this is the more common circuit that you see for a source follower. And the reason why I wanted to show you all this is because this came directly from the small signal model. But in a lot of books, you'll just see a source follower circuit looks like this, and you're not really necessarily given explicitly how you got there. But it just came from this. Okay, so this thing right here, this VGS equals VI plus VBS, allowed me to get this this generator in terms of CGD now instead of in terms of voltage across CGD instead of the voltage across VGS, and everything else kind of just fell into place where I simplified the generators to just be resistors by finding that the voltage across them was the controlling voltage. So I'm going to go ahead and stop here, and I'm going to pick up at this point next time and talk about input impedance, output impedance, and how you find those values. And for this circuit, there's quite a lot of complexity when you're finding a couple of those values, because I did include both CGS and CGD, and so that I'll try and get through that without bogging you down too much, but hopefully it'll be informative. So that's all I have for today. Thank you guys, and have a good weekend.
This concludes E5 PowerPoint discussion on Friday, June 21st, 2014.